Okay, hello everyone. Here is the official demo of the first topology-aware frequency domain distribution matching for Coreset selection in CVPR 2026, and it's a work done at XGTU. And here first, I would like to give you a brief introduction of this work. We have identified that the existing Coreset methods may suffer from several problems, and they could be separated into two parts. The first is the DN-based methods. They may suffer from the architectural bias and compromising generalization. And for the DN-free parts, okay, they typically use the heuristics such like radius theoretical grandies for stability and accuracy. And we have also discovered that the distributional equivalence is of vital importance for the performance of the downstream task of our Coreset. So we'll see in the left-hand side in this figure, we'll see the better the distributional equivalence and the better the performance is. Okay, we also identify that the prevalent distribution matrix like the KLCE or the MMD may suffer from the incapability of capturing the higher order moment difference. So we will see here, this is a really tiny illustration. Here is the ground truth distribution of our original dataset, and if we use MIZ to ensure the distributional equivalence, you will see here the performance is not it's actually not that good. You will see here is some mismatching, and it is same to the KL. We'll say there is also some mismatching components. And here in this work, we use the frequency domain is actually CFD characteristic function distance. We use it to depict the difference between the Coreset and the original data set. So you'll see here the distribution is equivalent. Okay. And we also identify that some problems of the naive CFD, and the most important or the most critical thing is the vanishing pace gradient problem in the standard CFD, where the pace magnitude coupling blinds the optimizer to medium and high frequency details. And here is an example of the bird picture, the picture of the bird, and we will see if we use a naive CFD, we will lose some of the high frequency details, and also some of the pace components, which is really important for the fine-grained features. And we also identify that the CFD, the frequency selection is really important for the CFD. So we have also introduced some techniques to manipulate this process. Okay, here is our method. We'll and it's actually comprised of the four main components. The first thing is the graph encoder. Actually, it is the spectral manifold construction. We just construct a multi-scale K-n graph, and it extracts the spectral manifold features using the normalized graph Laplacian. And we also design some of the graph structure-aware constructions to ensure the graph is equivalent to the original dataset. Is a really good representation of the original dataset. See here the matching constraint, the graph constraint, and also the diversity constraint. So after building this graph, and we just first initialize a smaller graph as our Coreset, and we just turn it into the frequency domain, and to use the PDCFD, which is we'll see here the pace decoupled frequency matching. And we could see the loss here, or the function here is actually decouple the pace component from the magnitude component. So here is also a parameter. It could be, and it's strong. It's correlated with the omega, the frequency omega, and it has been uh, separated in the different frequency bands. So we use the PDCFD to transfer or to project the graph in the spectral domain into the frequency domain, and we just use these characteristic function laws to depict or to constrain the distributional equivalence. And as we have just said, the frequency selection plays a vital role in this whole in the effectiveness of the PDCFD. So actually here we optimized a frequency band and we use a progressive sampling strategy. So it's actually here the curriculum scheduling mechanism, and we will select the different frequencies for different data sets. So actually it is a really adaptive approach. So here is our total loss, which contains the mean, our match, our graph, and our depth, right? Depth stands for the diversity. Okay. So here is our experiment, and we'll see our first actually performs well, and in this figure, we could see the y-axis is energy, stands for energy, and the x-axis is time. So we will see our CPU version. Our CPU version of the first is actually at the bottom left corner, and our age the first deployed on the edge devices could have a much lower energy consumption. Uh, and for the performance, which actually we'll see all of our two versions have the best accuracy. We'll have a really nice efficiency, right? It's at the top right corner. Yeah. And here is the comparison of different methods. And the bar here is actually the accuracy. It's accuracy, and the line here is alignment score, which is used to indicate the degree of distributional equivalence. So we will see actually they have a strong correlation here. The methods with a good with a higher alignment score may have a higher accuracy, although here is some small fluctuations, but we could see the overall trend here. And this figure is actually the generalization is a generalization ability of our method. So we will see in this line, you will see this line first outperform all the other methods. We could see some other baselines that the accuracy of them will drop for the different architectures. So that is our work. So hope you could enjoy it. Thank you.